At first glance, black holes appear to be cosmic garbage disposals, regions of spacetime so dense that nothing, not even light, can escape their pull. Anything that crosses the event horizon, the boundary beyond which escape is impossible, is seemingly lost forever. But this leads us directly into one of the deepest puzzles in modern physics, the black hole information paradox. At its heart lies a simple, profound question. What happens to information when it falls into a black hole? If it disappears completely, it would violate one of quantum theory's most sacred principles, that information is never destroyed. And that creates a paradox that has confounded physicists for decades. In quantum mechanics, information is encoded in the wave function of a system. Even when particles collide, decay, or transform, the overall evolution of the quantum state is supposed to be unitary, a reversible process where no information is truly lost. If you had perfect knowledge and enough computing power, you could, in theory, rewind any quantum interaction and recover the original state. But black holes appear to break this rule. When a book, a person, or a star falls into a black hole, all the complex information describing it, its position, structure, and quantum state seems to vanish behind the event horizon. Stephen Hawking made things worse or more interesting in the 1970s. He showed that black holes are not entirely black. They emit radiation due to quantum effects near the event horizon. This so-called Hawking radiation is thermal, random, and featureless. It carries no imprint of the material that fell in. Over immense timescales, this radiation causes black holes to evaporate, shrinking until they eventually vanish. But if the black hole disappears and the radiation contains no trace of the original information, then the information is truly gone, obliterated. That directly violates quantum mechanics. So, which theory is wrong? Quantum mechanics or general relativity? This is the paradox. Both are enormously successful, yet they seem to contradict each other in the extreme conditions of a black hole. Many physicists believe that a deeper, more unified theory, perhaps a theory of quantum gravity, will resolve this contradiction. But how? One idea is that information is not lost, but somehow encoded in the Hawking radiation in extremely subtle correlations. This view gains support from developments in quantum information theory and entanglement entropy. The concept of black hole complementarity suggests that information is both reflected at the horizon and also falls in, but no observer can see both, thus preserving consistency without contradiction. Another dramatic proposal is the holographic principle, stemming from string theory and championed by physicists like Gerard T. Hooft and Leonard Susskind. It suggests that everything that happens inside a black hole is encoded on its surface, just like a hologram stores 3D information on a 2D surface. In this view, the entire universe may be described as a projection of information encoded on a boundary, an idea that radically reshapes our concept of space and reality. Then came the firewall paradox, a challenge to the smoothness of spacetime at the event horizon. If information is somehow radiated back out, quantum theory might require that the horizon is not a gentle transition, but a searing wall of energy, destroying anything that tries to fall in. This idea is deeply unsettling because it contradicts the predictions of general relativity, which says an observer falling into a black hole would pass smoothly through the horizon, at least initially. So which do we give up? The smooth horizon, the conservation of information, or the principle that distant observers see consistent realities? Most recently, quantum gravity and holographic dualities have begun to shed new light. In particular, a technique called the replica wormhole calculation, used in the context of the ADA/CFT correspondence, a powerful realization of the holographic principle, suggests that information might indeed be recovered from Hawking radiation. This development marks a potential breakthrough, a semi-classical calculation that obeys unitarity, suggesting that information is not lost. Even in a fully evaporating black hole, the black hole's radiation becomes increasingly structured as it shrinks, potentially encoding the information that fell in. But practical questions remain. If the information is preserved in the Hawking radiation, how can it be decoded? Would it require a quantum computer the size of the galaxy to extract it? Does the information ever really leave the black hole in a usable form, or is it forever scrambled beyond recognition? So, does information that falls into a black hole disappear forever? If it does, quantum mechanics must be wrong. If it doesn't, we need new physics to explain how it escapes from what was thought to be a one-way door. The current consensus is shifting toward information preservation, but the full mechanism is still being unraveled. What began as a paradox has become a powerful window into the unification of gravity and quantum theory, perhaps leading us toward the long-sought theory of everything. Could solving the black hole information paradox reveal the true nature of space-time, gravity, and quantum reality itself? Increasingly, physicists believe the answer is yes. The black hole, once thought of as the end of knowledge, may instead be the key to its deepest secrets. The black hole information paradox arises from the conflict between general relativity and quantum mechanics regarding the fate of information that falls into a black hole. According to classical general relativity, black holes are regions from which nothing, not even light, can escape, suggesting that information is lost forever once it crosses the event horizon. In contrast, quantum mechanics is founded on the principle of unitarity, which requires that information is preserved in time. This paradox challenges our understanding of how fundamental laws of physics operate when extreme gravitational effects are involved. Example: when a star collapses into a black hole, all the details about its constituent particles appear to vanish behind the event horizon, leading to the paradox of lost information. Analogy, it's like shredding a document into confetti in a secure shredder. Classical theory suggests the information is gone, while quantum theory insists that the details must be recoverable in some form. The paradox is defined by the apparent loss of information when matter falls into a black hole, conflicting with the quantum principle of unitarity, which states that the evolution of a closed system is reversible and preserves information. In quantum mechanics, the complete description of a system must evolve in a way that no information about the initial state is irretrievably lost. However, classical descriptions of black holes imply that all information about infalling matter is permanently hidden behind the event horizon. This contradiction forces physicists to re-examine the nature of information and its conservation in extreme environments. Example: the theoretical disappearance of a particle's quantum state when it enters a black hole directly challenges the expectation that the state's full description should be recoverable from the system's analogy. It's like watching a movie where the final scenes suddenly cut off and the credits roll, leaving viewers with the unsettling feeling that key parts of the story have vanished forever. Stephen Hawking's prediction of black hole radiation introduced a mechanism by which black holes can lose mass over time, ultimately evaporating completely. Hawking radiation is thermal and appears to carry no information about the matter that originally formed the black hole. This leads to the conclusion that if a black hole evaporates entirely, the information about its initial state seems to be lost to the universe. Such a loss would violate the fundamental quantum mechanical principle that information is conserved in isolated systems. Example: calculations of Hawking radiation yield a black body spectrum that depends only on the black hole's mass, charge, and angular momentum, with no trace of the detailed information about the particles that fell in. Analogy, it's like burning a book and only being able to measure the heat and ash produced, without any way to reconstruct the story that was once written on its pages. Quantum mechanics is built on the principle of unitarity, which asserts that the evolution of a closed quantum system is reversible and that the total probability is conserved over time. This implies that all information about a system's initial state must be encoded in its final state, regardless of the processes that occur in between. The apparent loss of information in black hole evaporation thus poses a direct challenge to this principle. Reconciling black hole evaporation with unitarity is one of the key unsolved problems in theoretical physics. Example: in a unitary quantum process, if you start with a pure state, you must end with a pure state. But black hole evaporation seems to convert a pure state into a mixed thermal state. Analogy: it's like a perfect photocopy machine that should reproduce every detail of a document, Yet suddenly, parts of the text vanish in the final copy, contradicting its supposed accuracy. Various theoretical proposals have emerged to resolve the paradox, including black hole complementarity and the holographic principle. Black hole complementarity posits that information is both reflected at the event horizon and passes through it, with no observer able to witness both events simultaneously. The holographic principle suggests that all information contained within a volume of space can be represented as a theory on the boundary of that space. These ideas imply that information is not lost, but rather encoded in subtle ways that preserve unitarity even in the presence of black holes. Example, in the holographic model, a black hole's internal information is thought to be stored on its two-dimensional event horizon, analogous to a hologram that contains a three-dimensional image. Analogy, it's like having a high-definition two-dimensional blueprint that fully describes a complex three-dimensional building, ensuring no detail is lost, even if the structure seems inaccessible. The firewall hypothesis emerged as a controversial proposal suggesting that an energetic barrier, or firewall, forms at the event horizon, destroying infalling information and thereby preserving unitarity in a different way. This idea implies that an observer falling into a black hole would encounter a searing wall of radiation, contradicting the classical expectation of a smooth passage through the horizon. While the firewall model aims to resolve the paradox, it introduces new challenges and conflicts with the equivalence principle of general relativity. Thus, the hypothesis remains hotly debated in the theoretical community. Example, some theoretical models predict that black holes could develop firewalls that incinerate any information-bearing matter as it crosses the event horizon, radically altering our understanding of space-time near black holes. Analogy, it's like a seemingly invisible barrier that suddenly becomes a blazing wall when you try to pass through a doorway, defying the usual expectation of a gentle transition. Recent developments suggest that black holes may possess soft hair, subtle quantum excitations that can store information on the event horizon. These soft hair degrees of freedom related to low-energy soft particles might encode the details of what falls into a black hole without violating unitarity. Quantum entanglement between Hawking radiation and the soft hair could provide a mechanism for information recovery during evaporation. Such theories represent a promising frontier in resolving the paradox by reconciling black hole dynamics with quantum information theory. Example, new models propose that soft photons and gravitons emitted during black hole evaporation could carry the missing information, effectively tagging the radiation with the details of the infalling matter. Analogy, it's like leaving a series of faint fingerprints on a surface that, when collected together, can reconstruct the identity of the person who touched it, even though the person has long departed. Although the black hole information paradox is primarily a theoretical problem, ongoing observational efforts in astrophysics and gravitational wave astronomy may provide indirect evidence to inform its resolution. Precise measurements of black hole mergers and the radiation emitted in these events could reveal signatures consistent with information retention or loss. Advances in quantum gravity experiments and simulations also contribute valuable insights. While direct experimental tests remain challenging, the interplay between theory and observation continues to push the boundaries of our understanding. Example, observatories like LIGO and the Event Horizon Telescope are beginning to probe the extreme environments around black holes, potentially shedding light on how information might be preserved. Analogy, it's like trying to deduce the inner workings of a clock by listening to its ticks and examining its exposed gears, gradually piecing together a coherent picture from indirect clues. The black hole information paradox remains one of the most profound challenges at the intersection of quantum mechanics and general relativity, spurring research into quantum gravity and string theory. Future theoretical breakthroughs may come from unifying these frameworks into a single coherent theory where information conservation is manifest even in extreme gravitational fields. The resolution of the paradox will have far-reaching implications for our understanding of space-time, entropy, and the ultimate nature of reality. As researchers continue to develop new mathematical models and experimental probes, The paradox drives innovation and deepens our quest for a complete theory of the universe. Example, cutting-edge research in string theory and loop quantum gravity is actively investigating how microscopic degrees of freedom at the black hole horizon might encode information, potentially offering a roadmap to resolving the paradox. Analogy. It's like piecing together an ancient manuscript from scattered fragments where every new clue brings us closer to understanding a long-lost story that could rewrite the rules of reality.